Hi guys, welcome back. Today we're going to do our first real calculus lesson. Limits. Limits, that's a concept you started in pre-calc last year. You did a good bit with it in pre-calc even. But that was the end of the year, you may not remember. This is really actually the first calculus lesson. Good luck, here we go. All right, before we get started with limits, I want you to try to graph this on your own without a calculator. So hit pause and see if you can figure out how to graph it. If you give up graphing it by hand, then maybe try graphing it on your graphing calculator. But hit pause and see what you can do. Okay, hopefully you paused the video, and if you were in front of me in my class, this would be one of those moments where everybody's looking at each other like, do you know what to do? Do you know what to do? And to be honest, most people are usually clueless, so I did that to you on purpose. Here's a quick review of how this would work. Okay, so to graph this, maybe it would help. And again, this is an Algebra 2 topic, but it's a lot easier than you think. All right, to graph this, try factoring it and then see if maybe you can remember how to do it. The numerator would factor into x minus 3 times x plus 2. The denominator is still an x minus 3. And now those x minus 3's cancel. Maybe that gives you a hint. And the simplified equation is just the equation of a line, okay? So the graph of this equation and the graph of my simplified equation, they look almost exactly the same, okay? The only difference is this denominator messes it up. So if I were to graph my simplified equation, that's just the equation of a line. Y-intercept is at 2. Okay, slope is 1, so from that y-intercept we're going to go up 1 and over 1. There's another point. Up 1, over 1, another point. Up 1, over 1, another point. You know how to graph a line, and that would be this line. Okay, well that's this equation. The original equation, however, is slightly different because this denominator, remember you're never allowed to divide by 0. So if x were 3, that would give us division by 0. So how does that affect the graph? Maybe you remember what this means right here? Okay. When x is 3, since that leads to division by 0, it actually creates a hole in the graph. So when x is 3 on my graph, 1, 2, 3, if I go all the way up to my line up here, this point right here doesn't actually exist. There's literally a hole in the graph right there. All of these other points are the same, whether it's the original equation or the simplified equation. The only difference between the original equation and my simplified equation, the original equation has a hole in the graph, which is actually the beginning of the concept of limits. Okay, now I'm going to pause for a minute and get a prettier version of this graph before we continue talking about it. Okay, so here we are. This is the graph just a little bit neater so we can talk about it. All right, so again, this equation looks exactly like this equation, except there's literally a hole in the graph. All right, so what does that have to do with calculus? Well, sometimes you want to know that point that the graph is approaching, even if it doesn't quite reach it. In calculus, we would say, what is the limit as x approaches 3, since again, it can't actually equal 3. What is the limit as x approaches 3 of f of x if I renamed this f of x? Okay? All right, I want you to think of a limit, very, very easy definition. It's not really a definition. I just want you to think of a limit as the height the graph approaches, regardless of whether or not it actually reaches that height. Okay? A limit is the height the graph approaches from both sides, regardless of whether or not it actually reaches that point. So the limit as x approaches 3 would be the height at 3, which is 5, even though there isn't actually a value of the function. F of 3 does not equal 5 because there's no actual point there. Okay, algebraically, by the way, if you didn't have this graph, then if you plug the 3 into the simplified equation, it also would give you the value of that limit. Okay, so let me say it again. The limit is the height the graph approaches, regardless of whether or not it actually reaches that height. So what about these other limits? Okay, this is the same equation, same graph. Okay, we already discussed the limit as x approaches 3 is the height at 3. Even though there's a hole there, we are approaching a height of 5 from both sides, from the left and from the right. Well, what about at 5? The limit as x approaches 5 would be the height at 5, and that would be 7. So notice that a limit, the answer to a limit question, a limit can be a hole in the graph and it can be a solid point in the graph. Either way, because a limit is the height the graph approaches, regardless of whether or not it actually reaches that height. Okay? At -4, the limit as x approaches -4 would be the height at -4, which is -2. Okay, let's do a couple more just to make sure you understand. All right, here's another one, and with some new symbols that you may or may not remember. Okay? So, the first question says, what is the limit as x approaches -1 from the left? That little negative off to the side, that means from the left. So the limit as x approaches -1 from the left, that would be the height when x approaches -1 from the left side. So from the left side, as x approaches -1, the height appears to go to 2. Even though there's a hole there, it's approaching a height of 2 from the left. The limit as x approaches -1 from the right, that would also be 2, even though there's no actual point there. Now, that's the whole point of a limit. Mostly for limits, we're saying what is the height that we are approaching, even though we don't actually reach that height. We're approaching it from both sides. Now, if your left-hand limit and your right-hand limit are the same, then the overall limit exists. So the limit as x approaches -1 is also 2, because the left-hand limit and the right-hand limit would both 2. So if from the left and from the right you approach the same height, then the limit exists, and this limit was 2. Okay? Okay, how about at 2? Let's focus at the x-coordinate of 2. The limit as x approaches 2 from the left would be this guy, that hole in the graph, which is -3. Okay? The limit as x approaches 2 from the right would be -1. Notice this guy was a hole in the graph. This guy is a solid point. That's okay either way. The limit is the height the graph is approaching, regardless of whether or not it actually reaches that height. All right, now the limit as x approaches 2, since the left-hand limit and the right-hand limit weren't the same, this does not exist, and you write D and E, does not exist. See? Easy peasy. Let's do another one just to be sure. Okay? By the way, I wrote this PowerPoint ages ago, and I tried to make it so this little hole in the graph is actually on the graph. I could not fix it, and it was causing me pain. So pretend that that little hole in the graph is actually on the graph, which is where I wanted it to be. All right, here we go. The limit as x approaches -1. Okay, well, the left-hand limit is 3. The right-hand limit is 0, therefore this one does not exist. Think of it like this. The left-hand limit, the right-hand limit have to meet at the same spot. Okay, there can be a hole there or a solid point, but from the left, from the right, they have to meet at the same spot in order for the limit to exist. Okay, how about the limit as x approaches 3? Well, from the left, it appears to be From the left, we're approaching -2. From the left, we're approaching -2. From the right, we're approaching -2. Since the left and the right are meeting in the same spot, even though there's a hole there, the limit as x approaches 3 does exist, and it's the height. Remember, a limit is the height, the y-coordinate. Okay, now, would this answer change? Hold for the bell. Sorry, I'm at school. Okay, notice that this stray point just flew in. Okay, I added this little point. Now let's readdress this question. We said that the limit as x approaches 3 is -2. Does that answer change if I throw in a point right there? Okay, and hopefully you're saying no, because remember, the limit is the height the graph approaches, regardless of whether or not it reaches it. So this graph approaches a height of -2. Okay, this straight point right here does not affect the limit. What that straight point is, though, it's f of 3. At an x-coordinate of 3, the height of the graph is actually -3. Oops, extra negative I put in there. Okay, the height of the graph is -3. So f of 3 is -3, but the limit as x approaches 3 is not affected by that straight point. Okay, so f of 3 is a solid point. The limit can be both a point or a hole, but remember, it's the height you're approaching from both sides. Okay, one more time just to make sure you got it. Here we go, a whole bunch of high-speed questions. Okay, high speed. Limit as x approaches 1 from the left would be 0. Okay, the limit as x approaches 1 from the right would be 1. The limit as x approaches 1 overall would be DNE, because the left and the right aren't the same. Okay, how about at an x of 2? When x is 2, the limit as x approaches 2 from the left is 1. The limit as x approaches 2 from the right is 1. The limit as x approaches 2 overall is, they're the same, therefore 1. But how about f of 2? What is that? 2. Okay? So the limit is often the whole. A limit is the height it approaches from both sides. And this is the value of the function. Okay? Last one, how about at 3? The limit as x approaches 3 from the left would be 2. The limit as x approaches 3 from the right would also be 2. So the limit as x approaches 3 overall would be 2. What is f of 3? Also 2, the solid point. But these two things don't always have to be the same. Hopefully that's getting easy for you. Hopefully you get, it's not too bad of a concept. I hope it's not too bad. Okay, now I'd like you to do these next couple of problems. I'm going to show them here on the slide. I'd like you to try to do all of them completely on your own sheet of paper. And when you're done doing them, check them with my answers. Hit pause. Okay, check your answers. The limit as x approaches -3 from the left is 1. The limit as x approaches -3 from the right is also 1. And therefore, since it's the same, the overall limit is also 1. At 2, the limit as x approaches 2 from the left is -1. The limit as x approaches 2 from the right is +1. The overall limit does not exist since they don't meet. They're not the same. The left-hand limit does not equal the right-hand limit. Okay, try this one. Hit pause, and when you're done trying it, check your answers. Okay, let's see how you did. The limit as x approaches -2 is the height at -2, which is -1, or I should say it's the height it's approaching at -2, which is -1. The limit as x approaches 1 is 1. G of 1 is -1, the solid point. The limit as, oops, sorry, I got rid of it. Hold on. Okay, I don't know where I left off. Sorry, I deleted all that. Part D, the limit as x approaches 3 from the left is -1. the limit as x approaches 3 from the right is positive 1. And again, one of them is a solid point, one of them is a hole. It doesn't matter because it's the height it's approaching, regardless of whether or not it reaches it. But the overall limit at 3 does not exist because the left-hand limit and the right-hand limit are not the same. Hope you guys got 100 on that. I'm sure you did. Okay, now we're going to switch gears a little bit. This is the same problem we started the lesson with. And we were approaching the limit questions graphically. Now let's assume you don't have this pretty graph to look at, okay, and you're trying to answer the same questions. If you didn't have the graph to look at, when you evaluate a limit, your first approach is just to try to plug in an x of 3. Well, for this problem, if I plug in 3, I don't even have to look at the numerator. The denominator gives division by 0, so you can't do that. So you try to factor and cancel, and if you can factor and cancel, you try to plug in the 3 again. So we've already factored this before, so we know it factors into x minus 3, x plus 2. The x minus 3's cancel. And now I'm going to take this x coordinate of a 3 and plug it in, and the value of my limit is 3 plus 2, or 5. Graphically, remember that meant there's a hole at 5. Okay, well, how about this limit? I'm going to try to plug in a 5. I can either plug in the 5 here for all of these x's, or I can plug in the 5 here for the one x that remains. It doesn't matter because there's no hole in the graph. Whether I plug it into the simplified equation or the original, you're going to get the same answer either way, and that is 7. Graphically, it's because when x is 5, the height is 7. Okay, so when you're doing a limit algebraically without the graph, you just simply plug in this value of x if you can. If you can't plug it in because of division by 0, then you try factoring or some other algebraic trick that I'll show you soon in order to then plug it in after you simplify. So this one I would plug in a negative 4 for the x that used to be here, and you'd get negative 2. Okay, so from scratch, how about this guy? First approach, just try to plug this in. Okay, if I can plug in an x of 0, then that's it. That's the value of my limit. So for this one, there's no problem. I can plug in 0. And if I plug in 0, I get negative 3 over negative 2. So the value of this limit is 3/2. Now you should kind of try to figure out what does that mean. If nothing canceled and I didn't have to do any fancy work, then this means graphically there's a solid point at 0, 3/2. So this graphically means there's not a hole in the graph, there's just a solid point, and it has a height of 3/2 when x is 0. Okay? First approach, plug in this x if you can. All right, one more, I think. Okay, this one, can I plug in that negative 1 right now? No, because it gives a division of 0. So try to factor and then plug in the negative 1. No big deal. To factor this, this would be x minus 5 times x plus 1. The x plus 1's cancel. Now plug in my negative 1 for x. If x is negative 1, we get, if x is negative 1, we get negative 6. So, what does that mean? The answer to the question is negative 6. Graphically, it means that when x was negative 1, there's a hole at the point negative 1, negative 6. How do I know there was a hole? Because I had to cancel. Okay, when you cancel that factor, it means division of 0 would have happened. Okay, and so when x is negative 1, there's a hole at negative 1, and the height of that hole is negative 6. Okay, same thing here. The denominator, x can't be negative 1, but we're not asking about negative 1. I'm asking about 2. So I can use the simplified version, which I had from the previous problem, or I can plug in the 2 to the original problem. It doesn't matter. Either way, you'll get the same answer. So if I plug it in right now, it's a little bit more work. Plugging in a 2 for all of these x's, I'd get 4 minus 8 minus 5 all over 3. So negative 9 over 3, that would be what? Negative 3. If you have already factored it from the previous problem, okay, that definitely would have been quicker to plug it in here. Plugging in the 2 now, you still get negative 3. But my point here is you don't really have to factor and simplify unless the issue gives division by 0. Then you have no choice. Again, since this one, we plugged in the 2, there was a solid point at 2, negative 3. There's only a hole at the spot where that factor canceled. All right, hopefully that was a not too bad of a start. Lesson took a little longer than I had hoped. It's a little difficult to talk to myself while I'm teaching these things and I can't see your faces to guide me and help me with my speed. I hope you did well. We will work on this a little bit more on Monday. Good luck. Let me know if you have any questions. Bye.